Hello everyone. Welcome to lecture 3.5. We will be discussing thread scheduling in CUDA. The objective of this lecture is for students to learn how a CUDA kernel utilizes hardware execution resources. We're going to learn how the hardware assigns thread blocks to execution resources. We're going to learn about the implications of capacity constraints of execution resources. And we're also going to learn about zero overhead thread scheduling in GPUs. This slide shows a simplified picture of how CUDA threads are executed by CUDA devices. In the middle of the picture, we show a small example of a thread grid with only 8 thread blocks. Each of these thread blocks can execute in any order relative to each other, and the hardware is free to assign thread blocks to any processor at any time. So on the left-hand side, we show that we have a CUDA device with few execution resources. So the hardware will be executing a few thread blocks simultaneously and take longer to execute the thread grid. On the right-hand side, we show a device with more execution resources. Therefore, the hardware will be executing more thread blocks simultaneously and take less time to execute the thread blocks. So this way, the kernel can automatically benefit from increasing hardware devices, let's say, in each generation of GPU.
Now we can go into a bit more depth into how the hierarchy of threads and thread blocks is managed on GPU resources. The GPU is organized into streaming multiprocessors, or SMs. Threads are assigned to the SMs in block granularity. Up to 32 thread blocks can be assigned to each SM on the Volta architecture, and each SM can take up to 2,048 threads. The number of threads per block and total number of thread blocks is a configuration parameter subject to hardware constraints. For example, 8 blocks of 256 threads, or 4 blocks of 512 threads are both valid choices for the Volta architecture. The SMs maintain the indices of thread and block IDs and handle the management and scheduling of thread execution.
Recall each CUDA thread can be thought of as a processor in the von Neumann model. And the processor has a control unit that can fetch instructions and decode these instructions to control the processing unit to manipulate data, access memory, and so on. This slide shows a slight extension to the von Neumann model to implement a single instruction, multiple data unit or execution unit. So instead of having one processing unit, we have multiple processing units in the middle of the picture. And all these processing units are controlled by the same control unit. So the same control unit can fetch an instruction but it will control multiple processing units, and each of these processing units can manipulate a different piece of data and access different parts of the memory. Now that we understand the basic concept of single instruction multiple data execution, we can understand how warps are actually executed in streaming multiprocessors. Each block will be executed as a collection of 32 thread warps. If we have a 256 thread block, we are going to divide that thread block into 8 warps, each one with 32 threads. And this is an implementation decision, not part of the CUDA programming model. And these warps are scheduling units in SAM. Whenever any thread executes in SAM, all the other threads in the same warp will also be executing. And these threads in the same warp will execute in the single instruction multiple data manner. So all of them will be executing the same instruction at any point in time. The future GPUs may have different number of threads in each warp, so we should not assume that all the GPUs will always have warps with 32 threads. In this slide, we show the arrangement of execution of thread blocks in an SM in the context of warps. Let's say if we assign 3 blocks into a streaming multiprocessor, and each block has 256 threads. Then we know that each block is going to be divided into 8 warps of 32 threads each. And since we're assigning 3 blocks into each SM, we're going to have 8 warps from each block and 3 blocks. And we have a total of 24 warps executing in the streaming multiprocessor. And these 24 warps will be executing in the streaming multiprocessor by sharing the register file, the L1 cache, and the shared memory resources as we show in the green box in the bottom of the slide. Now that we understand how the thread blocks are assigned to SAMs and how the thread blocks are divided into warps, we can now explain how SAM actually executes these warps. During runtime, each SM implements zero overhead warp scheduling. At every clock cycle, the hardware keeps track of the status of operands for each instruction that will be executed next. Remember that every warp will be executing only one instruction among all the threads in the warp. So we're keeping track of the next instruction for all the threads in each warp. So the instruction that has its operands ready for consumption become eligible for execution, and therefore, some of the warps will have the next instruction with operands ready, and these are eligible warps. And the warps whose next instruction do not have all its operands ready are not eligible warps. So the eligible warps are selected for execution based on a prioritized scheduling policy. In GPUs with rich amount of resource, multiple warps could be selected for execution in each clock cycle. In GPUs with less execution resources, it can be only one warp selected for execution in each clock cycle. As we already mentioned, all the threads in a warp execute the same instruction when it's selected for execution.
This slide shows how one can reason about the thread block granularity that's most appropriate for organizing the execution of a kernel for a matrix multiplication problem. Consider using block sizes of 4x4, 8x8, or 30x30 threads. For the 4x4 case, we have a total of 16 threads per block. Each SM can take up to 2,048 threads, which translates to 128 blocks. However, the SM can only take up to 32 blocks total, so only 512 threads will go into each SM, 1/4 occupancy. For 8x8, we have 64 threads per block. Since each SM takes up to 2,048 threads, it can take up to 32 blocks and achieve full capacity, unless other resource considerations overrule. For the 30x30 case, each block would have 900 threads. Only 2 blocks could fit into an SM for Volta, since a third block would exceed the 2,048 total capacity. Therefore, only around 70 to 80% of the thread capacity of the SM would be utilized.
GPU programming. This is the end of the introduction to the toolkit. Thank you.